So today, we're going to dive into something pretty cool. We're going to explore how the teeny tiny random jumps of individual particles can actually show us the predictable large-scale behavior of a whole system. We're going to unpack a really fascinating model from physics called the symmetric simple exclusion process. But let's start with the big question. Think about it. Imagine a gas in a room. You've got trillions upon trillions of molecules just bouncing around like crazy. How on earth can we possibly predict what that whole system is going to do? It seems like pure chaos, right? Well, that exact problem is why we need models like the one we're looking at today. All right, here's our game plan. First, we'll connect the tiny world to the big one, from micro to macro. Then, we'll get into the rules of what I like to call the exclusion game. After that, we'll see where this game is played, we'll map out literally every possible move, and finally, we'll see why any of this actually matters. Okay, section 1, from micro to macro. This is all about bridging two completely different worlds, the world of the incredibly small and the world we can actually see and measure. You know, this whole idea goes way, way back. We're talking about pioneers like Ludwig Boltzmann. He developed this field called statistical mechanics, which was a revolutionary way of showing how the properties of single atoms, the micro stuff, actually determine the properties of the materials we interact with every day, the macro stuff. And here's the fundamental challenge, the real hurdle. It's literally impossible to track every single particle. There are just way too many. So the goal isn't to follow one little guy on its journey. Instead, the goal is to describe the big picture, things like density or pressure, based only on the simple local rules of how all those tiny particles bump into each other. So, how do we actually do that? Well, let's bring in the star of today's explainer, the symmetric simple exclusion process. You can just call it SSP. The best way to think about it is like a game with a very, very specific rulebook. At its core, the SSEP is a model for particles doing a random walk. They're basically just hopping around a bunch of different spots. But, and this is the most important part, their movement isn't a free-for-all. It's held back by some really specific restrictions. And the cool thing is, the name itself tells you all the rules of the game. First up, exclusion. This is simple. One particle per spot. If a neighboring site is already occupied, tough luck, you can't jump there. Second, simple. This means particles don't just teleport across the board. Nope, they can only hop to an immediate connected neighbor. And finally, symmetric. There's no preference for any direction. A particle is just as likely to jump left as it is to jump right. It's totally unbiased. So we have our particles and we have our rules. But where is this game actually being played? Well, this is where the idea of a network comes in. In the world of math, we call this playing field a graph. And don't let the name fool you, it's not super complicated. It's really just a set of dots, which we call vertices or sites, and a bunch of lines connecting them, which we call edges. This picture here shows it perfectly. Those circles, those are our particles, and they live on the vertices. The lines connecting them are the edges. Now, a particle can only travel along one of those lines to a neighboring spot, and of course, only if that spot is empty. That's our exclusion rule in action. All right, let's move on, because this is where all these simple ideas start to build into something much, much bigger. We're now going to map out every single possible move to unlock the power of something called the state graph. First, there's a word we need to know, configuration. All this means is a snapshot in time. It's like you hit the pause button and you see the exact arrangement of all the particles on the graph at that one instant. Every unique arrangement is what we call a state of the system. So, have a look here. On the left, we're in state A. Then one little particle makes one valid jump, and boom, over on the right, we're now in state B. Did you see that? A single microscopic event, one particle hopping one spot over, just changed the entire macroscopic state of the system. Now here comes the mind-bending part, and it's really important to get this. What if we figured out every single possible configuration the system could ever be in? And then, what if we drew lines for every possible jump that connects one of those states to another? We would create a giant interconnected map. But this isn't a map of physical places anymore, it's a map of abstract states. That map is the state graph. Which brings us to our last section. You might be wondering, okay, why would we go through all that trouble to build this enormous abstract map? What's the payoff? What secrets does it actually unlock? Well, by analyzing the structure of this states graph, we can do some incredibly powerful things. We can find the system's happy place, its equilibrium states that it naturally wants to settle into. We can calculate how fast it gets back to that equilibrium after it's been disturbed. And this is the big one, we can use it to model real-world transport, like the flow of energy or mass. And finally see, clearly, how a few simple microscopic rules lead to predictable macroscopic laws. And that leaves us with a final thought to chew on. We just saw how 3 super simple rules, exclusion, simple, and symmetric, can build a model that's powerful enough to describe the complex flow of particles. So the real question is, what other seemingly chaotic systems, maybe in biology or traffic flow or even economics, could we start to understand using this very same fundamental approach?